Perfect. All right. Thanks everybody for coming again. It is my pleasure to introduce Jay Yang, who will unmute himself and tell us about random monomial ideals. Jay.
Let me unmute myself and then go into presentation mode. I can't actually see the toolbar when I'm muted. So I actually can see chat. So because I have a dual monitor set up for teaching. So feel free to send messages in chat. I'll be able to see them. And thank you to the organizers for giving me this opportunity to speak. I'm going to talk about, so I'm a postdoc at the University of Minnesota. And as you might expect, I'm on the job market this year. And I'm going to discuss random monomial ideals. So this is not a single paper. This is actually a collection of papers. I'm going to talk mostly about my results, but I will mention briefly some other results on this field, on this topic. It's a relatively recent topic, but I think it's one that's quite interesting. So before we get into random monomial ideals, let's talk about random graphs briefly, because this is really the inspiration for this sort of technique. This probabilistic technique or random methods have been used in a lot of fields, but most famously, they've been used in random graphs. So the basic question you want to ask is, what does an average graph look like? But of course, you needed some definition of an average graph. So it's slightly better or slightly more reasonable to ask what a random graph looks like. Of course, this by itself is still not a very well-defined question because I haven't told you what random means. And the answer as to what random means is that there are many, many different choices to what random means. It depends on context. So a couple sort of three common types of random graphs. So there's the Erdos-Renyi random graph, which is the one that I'll be concerned with mostly. And probably the one that you think of if you think of a random graph, where you take n vertices and take each edge with probability p, right, with some probability p. You can, of course, then also talk about random regular graphs or random scale-free graphs. These are of particular interest to people who are trying to model sort of social networks or interaction networks. And one model is this Barabasky-Albert's model of a random scale-free network or random scale-free graph. So there's lots of different models depending on what you're trying to study, what parameters you want, and in some sense, what sort of types of results you want. What do you want to say about graphs? And so as a bit of flavor, let's look at probably one of the most famous theorems on random graphs, which is the connectivity result by Erdos and Renyi, which says that if essentially if the choice of p, so as usual here, p is a function of n, right? If p is greater than, well, there's a 1 plus epsilon, but essentially log n over n, then your random graph is going to be connected. And if p is less than that, your random graph is going to be disconnected, at least asymptotically. Again, all these results are asymptotic. You ask about what happens as some parameter goes off to infinity. And I forgot to write that there. So let's add that. As n goes to infinity, right? And so all of our results will also be, in some sense, asymptotic. They'll ask about results as some parameter goes off to infinity. Okay, so let's talk about random monomial ideals then, because this is the actual field of study which I've been working on. So there's been, the goal of this study is to construct useful models of random monomial ideals to sort of better understand the behavior of ideals. So useful can have many different meanings, but at the very least, the model should be interesting. So they should yield some reasonable family of ideals. And the hope is that their behavior actually models the behavior of sort of generic ideals in some sense, or not generic in the general sense, but generic in the English sense of a generic thing. So I mean it much more broadly than one might say a generic ideal. But to better understand the behavior of ideals, you want a model of ideals that tells you something about ideals. And so these are listed approximately in chronological order. The dates of publication obviously mess things up a bit. But The first paper on this that came out on arXiv was by Delora, Petrovic, Silverstein, Stasi, and Wilburne, and they looked. And these are not titles. These are my descriptions of these papers. They looked at what they called an Erritis-Renyi type random model for a random monomial ideal. And there they proved bounds about the dimension in particular, and they showed that this can be a meaningful field of study. At almost the same time, so we only put ours on arXiv a few months later. With Daniel Erman, we wrote about random monomial ideals that come not from sort of the Erritis-Renyi type model, but of random flag complexes from the Stanley-Reisner theory. And then there's been a series of papers since then that sort of build on this idea and develop this idea. So Delora, Hochster, Krohn, and Silverstein later then also looked at, this date is, this is a weird, I think there's a correct date for this, it's not 2018, that looked at the free resolutions of their Erritis-Renyi type random monomial ideals. And then more recently, there's been a result by Bandri and Yorgashawan, which looks at regularity of random edge ideals, which looks different, but I assure you that you can actually think of it as a special case of the model in the second paper. And more recently with Caitlin Booms, Daniel Erman, and myself, we've looked at torsion and syzygies, which I'll discuss, and degrees of random monomial ideals. And these are in two different models. So here we see that we have sort of two different models that we've been studying. One is this Erritis-Renyi type model, and one is this model coming from random flag complexes. And I'll discuss both in this talk, although I'll be a little bit briefer about the Erritis-Renyi type model. And this is not to say that these are the only two models you could choose. These are simply the two models that we have used and have results for. One can certainly think of other models for random monomial ideals, or even possibly random ideals, although it's a little harder to think about how one would construct them in that case. So a 5-second review of probability. You don't need to know these in detail. This talk is not really going to heavily rely on probabilistic methods details, although the papers do use a lot of probabilistic methods details. This P of A is the probability of some event A. This term asymptotically almost surely means that in the limit, the event occurs with probability 1, right? Or rather, the probability goes to 1 as some parameter goes to infinity. And then there's this last term, convergence in probability, which essentially says that some random variable, some value that depends on randomness, converges to some value, some fixed value, or possibly some other distribution. But in particular, we're going to talk about relative to a fixed value. And it's just saying in this case that the value should be within epsilon in the limit. So these are terms we'll use, and so I want to define them and make sure they're here. But in some sense, their meaning is intuitive, and you can get into the details about how to prove things with them. But as far as understanding the results, their meaning is relatively intuitive.
Sorry, can I ask a question?
Yeah.
Is there maybe a typo on the last line where you're defining convergence in probability? Is that really goes to 0 or goes to 1?
1. I probably had it reversed. I had probably had an inequality reversed at some point, and then I copied it and unreversed the inequality or something. Thank you.
Thank you.
Right. Okay. So let's first talk about this Erritis-Renyi type random monomial ideal. So this was, again, first defined by Delora, Petrovic, Silverstein, Stasi, and Wilburne. And their model is basically to say, let's take all of the monomials in some polynomial ring of degree at most d, and do the same thing that the Erritis-Renyi model of a random graph does. Although Erritis and Renyi themselves did a slightly different variant of it, which is to say, each monomial, we say this is in our ideal. We force this monomial to be an ideal, i.e. it's a generator, possibly redundant, with some probability p. And then we ask, what is the behavior of a random ideal in this model as d goes to infinity? Here, the parameter that we're going to care about going to infinity is d. You could ask about what happens as n goes to infinity as well, but in this case, we've chosen to ask what d goes to infinity, what happens as d goes to infinity. And then, of course, p will be a function of d and will depend on d. Okay. So again, the original paper discussed dimension bounds, but more recently with Silverstein and Wilburne, who were both co-authors on the original paper on the Erasmus-Renyi type model, we've looked at what is the degree of a random monomial ideal in this model. And so the way we actually approach this is we can constrain very strongly what's known as the staircase diagram for the ideal. So this is the theorem, and it looks like a lot of text, but the main thrust of this theorem, which I'll illustrate on the next slide, is that we can, this is the generators. Whoopsies, I'm not in drawing mode. This here is the generators. And we can strongly constrain where the generators have to show up with high asymptotically almost surely, or in the limit, or at infinity in some sense. And so what does this theorem actually look like? Because the text is a little bit dense. What we're saying is if I take a random monomial ideal, and these are its generators, and I can draw the staircase diagram, which is just everything above here is in the ideal. So everything in this blue region is in the ideal. I should make it more obvious. Everything in this blue region is in the ideal, and everything below this blue region is not in the ideal. So this is a plot of all of the monomials, in this case, in k adjoint x1, x2. Right? And so what this theorem is saying is the staircase diagram is actually constrained between sort of two hyperbolas. So asymptotically, you can guarantee that these hyperbolas move, of course, but along with d, but you can guarantee in some sense that the staircase diagram lives between two hyperbolas. Right? So what does this give us? Well, it gives us actually a lot. We can constrain quite a few properties of the ideal, but the simplest property we can constrain using this construction is the degree. Right? So this is where sort of the actual main theorem of that paper comes in, which is that we can constrain the degree of a random monomial ideal by these two parameters, which, if you notice, up to an epsilon are the same. So we have a plus epsilon and we have a minus epsilon in the exponent in this case. But we've basically told you that the degree is approximately d to the k, well, k minus, let me write out the notation, floor k, log of d, all to the n minus 1. Right? So we've told you asymptotically what the degree is, with some caveats. There's some epsilons, and we do have to have the epsilon. We can't get rid, we can't completely get rid of the epsilons. So this gives a flavor of the sorts of results you can get constraining these random monomial ideals. And this model has a lot of flexibility. Again, there's 3 parameters, and you can even change exactly how you interpret these parameters. And so there's a lot to be studied with this model still. And there's a lot we don't know about this model. But in this paper, what we looked at specifically was degree and standard pairs. And for that, this hyperbola law is sufficient. Okay, so let's discuss the other model of random monomial ideals. And so this will be a longer discussion because this one is, while the construction in some sense is equally simple, the results are a little bit more involved, at least in my opinion. So let's talk about random flag complexes. So a flag complex is a simplicial complex that's maximal among simplicial complexes with a fixed 1 skeleton. Another way to say it is you take a graph and you add every cell that you can without adding edges, and that's a flag complex. Right? And so the point of this flag complex construction is that you can take a random graph and immediately construct a random simplicial complex simply by taking a random flag complex associated with it. And this gives an interesting model of a random simplicial complex. And in fact, this is a model that's been studied. Sorry, backing up, I should show the example. I forgot the example was here. So let's say n is 6, right? And so I've drawn these in some order because my example looks like this. And then I can choose random edges. And this will be a random graph. This one's not actually that random, but let's ignore that. And you have a random graph, and you could study the properties of the random graph, but we really want a random simplicial complex. So what we do is fill in every cell that we can, right? So we fill in that cell. I forgot that. Okay, yeah. Right, and so this gives you a random simplicial complex. Remember, we want a simplicial complex, so we can't fill in this 1, 2, 3, 4 cycle because that would require adding an edge, and we're not allowed to add edges. So this is a random flag complex, and this has been studied. This has been studied before by people who study random topology. In particular, Matthew Cale proved a result which provides an analog to sort of the Erman connectivity result by instead asking about reduced homology. Right? You can phrase the Erman connectivity result as homology disappears above a certain point. Right? And so you can ask about when does homology appear and disappear for higher homology, not just H0. Right? Okay. And the other big component that we're going to need for this is Stanley-Reisner ideals. So in the study of monomial ideals, this is a very common topic. So the way I'm going to present it is, given a simplicial complex, we can construct the associated Stanley-Reisner ideal. And how do we do that? So I've taken a different example because it's simpler and I can demonstrate things a little bit easier. But let's take this simplicial complex here. This simplicial complex, this cycle here is not filled in. So this is not a flag complex. Well, then to it, we can associate via this SR correspondence, Stanley-Reisner correspondence, an ideal, a monomial ideal. And the way we do that is take the non-faces, the minimal non-faces. So you could also just take all non-faces, but the minimal non-faces are a generating set. And so for instance, let me use a different color. This green non-edge, right, it's not there, gives us this first generator. And this red non-filled in region here, it's a little awkward to draw, but that region gives us that generator. And you can keep doing this. In this case, there's just 3 minimal non-faces that you can check. And the reason this is an interesting correspondence, besides taking simplicial complexes, which we now know we have a random model for, and giving us ideals, which we wanted a random model for, this correspondence is actually a one-to-one correspondence for between square free. So the set here is square free monomial ideals and this is simplicial complexes. And this correspondence is one-to-one. And as we'll see, a lot of the properties of square-free monomial ideals are inherited by simplicial complexes and vice versa. And this will be very important to our ability to actually do something, right? Okay. So that leads us naturally to our model of a random Stanley-Reisner ideal. So a random Stanley-Reisner ideal is the distribution on ideals given by taking the Stanley-Reisner ideal associated to a random flag complex. At least that's our definition. There are, by the way, other models of random simplicial complexes. So there are many models of random simplicial complexes. And if you use a different model of a random simplicial complex, you may get other interesting models of random ideals. It's simply something we haven't studied. Okay, so let's go back to that example. And let's take the minimal non-faces. And as I said, it's a little bit more complicated, but we can take a couple pieces of it and see where they come from. So this 1, 3 comes from this edge. Right? This 4, 6 comes from this edge, or this non-edge. I should use a different color. Oh, well, I already used it, did it. And notice that neither of these edges exist. So let me put a cross on them just to emphasize that neither of these edges exist. Is this just the same as, yeah, so this is the same as taking the non-edges, and this is the point about why this is actually the same as a edge ideal. This is not something we realized initially, but there is a reason to go through so the point is, and Anton, you raise a good point, which is something I was about to mention, which is there's a coincidence you might notice, which is this is quadratic. This monomial ideal is generated by quadratics. And so actually, if you have a flag complex, the associated Stanley-Reisner ideal is quadratic, generated by quadratics. And so our model is not a model of all random monomial ideals. And in some sense, it's not even necessarily a model of all square-free monomial ideals. Our model best represents, things that look like monomial ideals with quadratic generators. Right? But again, the point of these models is to study something about ideals. No model has to cover the entire space of ideals uniformly in any sense. But yeah, thank you for the question. Okay. So then the natural question to ask is, what is the behavior of these Stanley-Reisner ideals associated to a random flag complex as n goes to infinity, right? That's sort of the question we've been asking for every model, is we take our parameter to infinity, and what can we say about its behavior, right? Okay. And so to answer this question, I need to go on yet another tangent, because we need to know what question we're asking before we can ask the question. So let's talk about Syzygies. So given that this is in some sense a commutative algebra and homological algebra seminar, I'm sure many of you are reasonably familiar, but let's go over it anyways. So we're going to talk about our Betty numbers, which come from the dimension of certain Tor modules, Tor of our module against the field. Right? So the usual way to compute this, of course, is to take a resolution of the module, and then these dimensions, this is dimension over the field, by the way, these dimensions simply read off the degrees of the graded components of the free resolution, the minimal free resolution. Right? And as a convenience, we often arrange these Betty numbers in a table, but it's not the usual table that you might expect if you had something indexed by I and j. There's an offset because it turns out certain entries have to be 0. And so the first row is actually given by, well, the 0th row, properly speaking, is actually given by beta 0, 0 and beta 1, 1 and beta 2, 2. The way you can think about this is the difference between the I and the j is 0. And the difference here between the I and j is 1. Right? So we get a table. This is what Macaulay 2 would spit out if you asked it for a Betty, if you asked it for the Betty diagram of a Betty table of a resolution. Right? Okay. So now, as we've seen, everything we've done is asymptotic. So the next step is to add the word asymptotic in front of Syzygies. So we're now going to talk about asymptotic Syzygies. And now this is not a new topic. This is a topic which has been studied before in the more direct sense. You ask for a family of modules or a family of ideals. In this case, we're going to care about with increasing projective dimension. What can be said about the behavior of the Betty numbers? What can be said about the behavior of the Betty tables as our parameter goes off to infinity, right? And so on this front, Ein and Lauzerfeld in 2012 proved this result, this perhaps surprising result if you're sort of used to NP type results, which basically says that at least for those modules which are homogeneous coordinate rings of smooth projective varieties embedded by ample divisors, the Betty table is as full as possible. And what do I mean by as full as possible? Well, I have this parameter here, rho sub k of our module. And what happens is that in the limit, this rho sub k, which represents the density of the kth row of the Betti table, right, the number of non-zero Betti entries in that row divided by the projective dimension plus 1 to deal with the off by 1. Well, this number actually goes to 1 as n goes to infinity. So that row of the Betti table has almost every entry you could have. And this is in contrast to sort of NP results, which usually say that the Betti table vanishes up to a certain point. Now we're saying that the row of the Betti table is actually almost entirely full. So it's in some sense a surprising result. And in the time since then, there have actually been many results which extend this to various slight generalizations, mostly dealing with relaxing the smooth condition or and giving allowing for things like arithmetically Cohen-Macaulay. But our approach is going to be different. We're going to translate this problem into a random monomial ideals problem. We're going to ask what happens, what about random monomial ideals? What if we take our model of a random monomial ideal coming from a random flag complex? What can we say about the Betti table as n goes to infinity? And perhaps surprisingly, well, or perhaps not, depending on whether you expect that the Ein-Laserfeld result is sort of true uniformly, we get the same type of result, which says essentially that up to some row where it cuts off, every row that we have has density 1 in limit, with a couple caveats. I do have to add this word in probability because we're dealing with random variables. And so the things involved here are random variables. And so you have to be a little bit careful about what you mean by going off to 1. But certainly this implies the expected density goes to 1. But it implies something stronger than simply saying the expected density goes to 1. It implies sort of almost all choices go to 1. Okay. So it's worth noting that the theorem we proved is not this theorem directly, but rather we proved what we can call a threshold result. We said for any particular Betti entry, so you fix some Betti entry with some complicated parameters, below some probability, that Betti entry is 0. If P is too small, that Betti entry is 0. If P is sufficiently large, though, that Betti entry is non-zero. And so what we get is this nice diagram. So if this is our Betti table, then what we have is this entire region where things are uniformly non-zero. So up here, everything is uniformly non-zero. And you can actually prove sort of that whole region is all non-zero with probability 1 all at once, up to, of course, the projective dimension cutoff, which I haven't shown. Below that, our result proves that the individual, up to some other cutoff, which I haven't shown, our result can prove that the individual entries are 0. And only after you get past the dimension bound on the regularity, then you can say that the individual entry, not only the individual entries are 0, but everything outside of this region, this trapezoidal region, is actually just 0 with probability 1, sort of uniformly. You might also notice here that this slope, that's because this is causal, because it's a monomial ideal generated by quadratics. So everything over here is also 0. So these are the sorts of results that we actually ended up proving. This is much more reminiscent of the random graph results, where you say something occurs with probability 1 or probability 0. So you're saying something occurs asymptotically almost surely in some regime, and asymptotically, the complementary result is asymptotically almost surely on the complementary regime. And so this fact is that we've gotten the same behavior out of our model of random monomial ideals and this sort of class of non-random families of ideals says to us that there maybe is a heuristic here. There's a heuristic that says that the asymptotic behavior of Betti tables for embeddings of smooth projective varieties should resemble without defining what that means, that of a random Stanley-Reisner ideal, where we mean a random Stanley-Reisner ideal in this model. Right? And as further evidence of this, let's look at this theorem. So I won't go into excruciating detail, but we had to fix much more constrained parameters here, you'll notice. But in this set of parameters, we actually get something that we can call the normal distribution of the quadratic strand. So if we look at the Betti table of the Betti numbers on the quadratic strand of our Betti table, and we normalize them, we have to normalize them because they're enormous, then they look like a binomial coefficient. In other words, when we divide by the binomial coefficient plus some constants, we actually get that it limits to 1. Again, in probability, there's some care required, and there's some care required about how you set this statement up. But it's saying that that quadratic strand of our Betti table actually looks like a normal distribution. And this is actually very similar to a normal distribution result in a paper by Erman and Lazarsfeld in 2015. Again, in that case, about embeddings of smooth projective varieties. And so this is further evidence that the two have very similar features. Again, there's no theorem here that says the two have the same features. It's just suggestive that the random model might be telling us something about the non-random case. Okay. And that leads into our next paper, which is with Caytlin Booms and Daniel Erman. So this is joint with Caytlin Booms and Daniel Erman, which asks about torsion. And what do I mean by torsion? Because you don't usually hear the word torsion when you talk about syzygies. So another way I could phrase what I mean is characteristic dependence. So if I have a module that's actually secretly defined over the polynomial ring over the integers, right? And then I consider it over a field, right? I can ask, when does this depend on the characteristic of the field? In that case, we're going to say that the Betti table, which I'm just going to write beta of the module, has torsion or depends on characteristic. And this is a surprisingly, well, it's a surprisingly unknown question, and that as far as we can tell, there's not that much known in general about when this happens. There's obvious cases when the module itself depends really heavily on characteristic, if your module has a 2 in its definition. But even in non-obvious cases, you can get sort of torsion appearing in the Betti table. For instance, the Vertices module of PR embedded by degree D, well, if R is greater than 6 and D equals 2, via a collection of papers, we actually know quite a bit about those cases. We know many characteristics and many primes over which the torsion, over which the Betti table would be different in that characteristic. But on the other hand, if you look just at P1, then for any D, there's no torsion because the Egon-Roth complex actually doesn't depend on characteristic. And so that always resolves it. And so that gives you your Betti tables independent of characteristic. And so, and as far as we can tell, outside of these two cases for Veronese modules, nothing is known. Nothing is known about the characteristic dependence. But this is where random methods really excel, in that we can really, not perfectly, but we can really show that in a large regime, these Betti tables do depend on characteristic. They do have torsion. So if we have a random flag complex, the question is, for a field, when does this depend on the characteristic of K? And a good thing to note here is that the Betti table can actually only depend on characteristic. It can't depend on the other properties of the field. It turns out that none of the other properties of the field will matter. Only the characteristic will matter. Right. So what we prove is that for any prime, I should really say prime, and so we take our random flag complex, take our random Stanley-Reisner ideal associated with it, then asymptotically, almost surely, the Betti table has torsion in that prime. So it differs in that characteristic relative to characteristic 0. This lower bound, by the way, we'll see where this comes from, and we don't expect it to be tight. So you might notice that this is not a threshold result. So this is why I wanted to point out threshold results earlier and contrast this. This is not a threshold result. We do not have a threshold result yet. There is some threshold, but we don't know it. So the tool we're going to use for this, as if you've seen Stanley-Reisner ideals, you probably expect that this is the right tool, is Hochster's formula. So what Hochster's formula tells us is that actually for a Stanley-Reisner ideal, the Betty tables of the corresponding quotient ring, the module given by S mod I delta, these are actually controlled by the homologies, the actual reduced simplicial homologies of subcomplexes of my simplicial complex. So this Betty table, which is a homology of sorts, is controlled by actual homologies of simplicial complexes. All right. And so more explicitly, let's take a look at what this actually means, right? So this beta, this entry here is beta 2, 4. So this one, actually, what Hochster's formula will tell you is I need a subcomplex of size 4. So I need 4 vertices, an induced subcomplex of size 4. I need 4 vertices, and this 2 will tell us that I need H1. It's off by 1, but we need H1 on 4 vertices. And if you look at this, there's one subgraph right here, which has H1 and has 4 vertices. So this has H1 is 1. And so this gives you this entry 1 right here. Or as another example, let's take this one here. This is beta 1, 5. And yeah, okay. All right, so what this is telling me is I need to look for a subcomplex. I should really do this in a different color. So this is beta 1, 5. And what this is telling me is I need to look for a subcomplex of size 5 with 5 vertices, which is disconnected. And of course, that's this subcomplex. This is a little less obvious, but it's still not hard to see. But the subcomplex outlined in green is disconnected, as exactly 2 components, and hence the 1. And it has 5 vertices. And it's, in fact, the only subcomplex with 5 vertices that's disconnected. And so every entry can be computed in this way by repeating this procedure. Okay. So what does this tell us? This tells us how to prove this result. This tells us how to prove most results about our model, which is that if we want to find some property of the Betty table, one way we can approach this is, since the induced subgraphs control what the Betty table looks like, we want to find a small enough subgraph, so small enough type of graph that has the right homology, has our, in this case, characteristic dependent homology. And then we need to show that that subgraph actually does appear, right? That it's not, that it appears with probability 1 in the limit, right? And so our tool here is this essential density. So this is our measure of small. So we want a graph with actually a small essential density. And the essential density is just the, so you can talk about the density as the average, you can talk about the density as the number of edges divided by the number of vertices. Right? How many vertices what is the average degree? And the essential density is simply the maximum of that density over all subgraphs, all induced subgraphs. I have to say induced subgraphs, otherwise I actually think it doesn't matter here because you're only ever decreasing the density. But either way, all induced subgraphs. And there's a special case, of course, where you're known as strictly balanced if actually the essential density of the whole graph equals, the density of the whole graph equals the essential density. the graph itself is maximal density. Those are the nicest cases. And so the way we use this essential density property is we look at these this proposition. So this proposition is actually based on a very similar theorem by Bolabas. The only difference between our theorem and his theorem really is that we want to talk about induced subgraphs. And as far as we could tell, there wasn't an easy way to abstractly translate it. So we just translated the proof. We actually didn't translate his proof. We translated another proof because his proof uses different techniques than a modern proof would use. But it's the same idea in the core. What it's saying is that the appearance of a particular subgraph, in this case induced, is controlled by the essential density, right? So if P is less than sort of n to -1 over the essential density of the graph we're trying to have show up, then the graph won't show up, right? If P is too small relative to the number of edges that this graph requires, then the graph won't show up. But if P is large enough, the graph is guaranteed to show up, right? And so this is what we need, right? We need a result that tells us when subgraphs appear, because now if a subgraph appears, that contributes, and it has a certain homology, that contributes to our Betti table, and that contributes to our Betti table in the right way, right? So our goal now is to find an actual graph with the right properties, such that the corresponding flag complex has torsion in its homology. So the simplest version of this is, of course, two torsion. Right? There's a very canonical topological space with two torsion, RP2. Right? And H1 of RP2 is Z mod 2Z. Right? This is a pretty commonly known fact. And the only thing that we have to be careful of is we have to give a flag triangulation, right? And so this is actually a reasonably well-known flag triangulation of RP2. There's actually a couple of different variants of it, but this is one variant of it. And you can verify its flag. It takes a little bit of work, but you can verify that sort of there's no triangles that need to be filled in, and there's no simplices that need to be filled in. And it turns out in this case, as you might expect from sort of the dense structure and the symmetry, that this graph is actually strictly balanced. And we computed MG by brute force, and it's 30 over 11. Right? So what does this tell us? Plugging this back into the machinery, right? We have all this machinery that tells us how to deal with the scenario once we have a graph, and that machinery tells us that if we're in this regime between n to the -11 over 30 and sort of a constant minus epsilon, or rather you can think of this as a constant, then asymptotically almost surely the Betti table actually has two torsion, right? It depends on, it's different in characteristic 2 than it is in characteristic 0. It's different in characteristic 2 because there are subgraphs which are this homeomorphic to RP2, right? Sorry, not subgraphs, subcomplexes, induced subcomplexes that have the same homology as RP2, right? In fact, they're the same as RP2 in some sense. Right, and so in some sense we've succeeded, and we can say, okay, we're done. But actually this tool can go a little farther if we're just clever with how we set up the graphs. And here it's also worth mentioning that the Bolabas result is a threshold result. And so it does tell you that below n to the -11 over 30, this subgraph does not appear. But what we didn't manage to show, and are not entirely certain how to show, but we suspect to be true at least in the two torsion case, is that there shouldn't be any way of getting a simplicial complex, so a flag complex with lower essential density than than 11 over 30. Again, sorry, 30 over 11, it's reversed, it's a 1 over. But we don't know how to show that, and that's why this result, even with the threshold result before, is not a threshold result. We can't prove that there doesn't exist some smaller graph which also gives a flag complex with 2 torsion. Right. So let's try to find other torsion. Right. In fact, let's try to find any torsion. Right. So the goal here is we're going to construct a simplicial complex that has some prescribed, has in its homology some prescribed torsion group. Right. And I should really say this is homology over Z. So this technique is based on a technique in a paper by Andrew Newman in 2018, where he constructs a non-flag simplicial complex with prescribed homology. So his question was just, how do I construct simplicial complexes that have prescribed homology? So we've taken his technique and we've just added the word flag to it and been careful about how we do it so that we actually get a flag complex and not just a simplicial complex. So the key observation in this method is that you can do this binary decomposition on this M, and then Z mod MZ is actually isomorphic to this group given by these generators. It's a little bit complicated and messy, but it's given by these generators and relations. And then we can realize these generators and relations on a sphere. So we take a sphere, we construct the right number of punctures, and then we glue the punctures in the right way, right? And then we have to do this all very carefully in a way that gives a flag triangulation and not just a triangulation. And so the first step is to construct a sphere with holes. Right? So you take your this thing. First step is actually not a flag complex of note, but the second step, T1, is a flag complex already. And so at every step, we preserve that property of being a flag complex. Right? After T1, at every step, it is a flag complex. Right? So that gives us a flag complex. That gives us a flag complex, which is a sphere. Right? And then the way we punch a hole in it is we use barycentric subdivision. So everywhere we need a hole, we use, well, not barycentric subdivision, but subdivision. So everywhere we need a hole, we insert this, we replace a face with this complex. Everywhere we don't need a hole, we replace a face with this complex. Right? So we repeat this and we get a sphere with holes. Right? That was our step 1. Right? And we can verify that that sphere with holes, because of the way we've constructed it, is actually flag. And in particular, you might notice that this hole is square. And it's important the hole is square, because otherwise it would be forced to be filled in. If it was a triangle, it would be forced to be filled in. Right? Now we need to glue these holes together. So that's where we use these so-called telescopes. So this is a 2-to-1 gluing, right? So you glue one side of this to one hole and the other side of this to the other hole by a 2-to-1 map. And again, we've been careful here in the way we glue this and the way we set it up so that everything inside is flag. Right? And then you glue all this together and then you get this. So the worst case, the largest degree vertices in this construction, which I'm not going to try to show an example of because even the smallest examples are messy, have degrees 12 and 14. I mentioned 12 for a reason, and we'll get to that later. So if we use this construction as is, we get this following theorem. And this is actually the initial theorem we had when we were starting to finish the paper. And it says that it's a random flag complex for this parameter when p is greater than n to the negative 1/7. And then in that case, asymptotically, almost surely, the Betti table has L torsion. Right? For any L. Right? This compared to 2 torsion before, this has L torsion for any L. And but we can actually do slightly better through a pretty trivial modification to our construction. So this degree 14 vertex looks like this. It looks like a mess, but the important thing is we can actually make it into 2 degree 9 vertices. I believe they're both degree 9. And that's what I got last time I counted. We have to be a little bit careful because we do increase some of the neighboring vertices degrees. But if you're careful, you get 2 degree 9 vertices and a couple vertices that go to degree 7 instead of degree 6. Importantly, what's left is degree 12 vertices. The maximum degree that appears is degree 12. And so that tells us that our essential density can't possibly be larger than 6. Right? And so what we get is the theorem I showed earlier, which says that if we, for any prime L and our random flag complex, our random monomial ideal, for p greater than sort of n to the negative 1/6, asymptotically almost surely the Betty table has L torsion. Okay. So heuristically, this should tell us that for some reasonable class of families of modules, which we haven't tried to define precisely in this case, as n goes to infinity, the number of primes such that the Betty table has L torsion is actually unbounded. This is our heuristic. Or a weaker version of this heuristic might be that for any prime, you eventually have torsion in any family, but maybe sporadically, maybe like every other module. You don't know that for sure. We don't know this. We don't have any strong evidence of this outside of the random results. Certainly there are families of modules where this doesn't occur. Again, we saw that with the Veronese of P1. But we sort of don't expect the Veronese of P1 to have it, because if we plug this parameter back into the paper on the vanishing of the Betty table, we actually sort of expect this Betty table to be this module to be regularity 6 or higher, or is it 7 or higher? I might be off by 1. And so you actually don't expect that P1, this heuristic wouldn't expect that P1 would have torsion. So it does match up, but we would really love if there were any examples, like any actual families of reasonable modules where you can show that actually the number of primes where the Betty table has L torsion is unbounded, or even quite frankly, where you can show that there is some prime where the L torsion is where there is L torsion asymptotically. Okay, so I'm going to conclude there. There's still a lot of questions that can be asked about random monomial ideals, and I think there's a lot of questions I hope to still ask. But that's the end of my talk, and if there's any questions, I'd love to answer them.
Let's use our reactions to thank Jay. And are there any questions for Jay? You can either unmute yourself and ask or put them in the chat. Yeah, I was going to say.
So I have a question. Well, okay. So you were saying there are many things you can still ask.
Yeah.
So is there any hope of answering things like talking about properties of the ring that your random monomial ideals define? So maybe the first thing to ask me would be Gorensteinness, since it's something you can see.
So you're asking, instead
Betty
of asking
table
about the module, let's ask about actually let's ask mod I as a ring.
Right.
I don't know. I haven't thought about it very hard. But certainly it should be doable. So like I can tell you some things, but they're still about the module. So I've never studied what the ring looks like. That's the short answer. But there's many results I didn't mention here from the original the first paper on this. Like this thing is actually never Cohen-Macaulay basically, but actually it's sort of very close to Cohen-Macaulay in that the projected dimension, the codimension are never far from each other. So you can get these sort of homological results, and Gorenstein is in some sense a homological result, although it's not, again, it's a little bit, I feel like this is an unsatisfying answer because I don't know the answer, but you can certainly ask this question. And I would love to see if there's interesting results on this front. Does that answer it?
So if from what you were saying, does it mean that, you know, to like asymptotically almost surely you get something that is not Cohen-Macaulay? Is that,
yeah, so
is
this
that one of the
module
results?
here is asymptotically almost surely not Cohen-Macaulay in basically any reasonable regime. The reason you can see this is sort of you're going to so to be Cohen-Macaulay, basically you would have to have that I can't remember the proof off the top of my head, but basically you can think about the very end of the Betti table and talk about the entries there, and those entries sort of are very close to the sort of dimension bound, and then you find that you just can't. There's not enough space to make homology.
I think you want to use Ausland or Buchsbaum, right? You want to. That's what you're saying. I mean, I think
I should just phrase it that way. You can compute the codimension of this thing because you can compute the dimension asymptotically, and you can bound the projective dimension, and you can show that there's a gap.
So correct me if I'm wrong. You can show that projected dimension is at least like n minus curl dimension over 2 or something, right?
Yeah. So, yeah, I'd have to look at the original paper to remember exactly what we argued. But there's a gap between them. But the gap is, I don't want to say the gap is constant because we didn't prove that, but the gap is O of n, little o of n. And so that's why sort of it's the ratio between the projective dimension and the codimension is 1. But it's never a Cohen-Macaulay.
Yeah, but in this regime, the curl dimension's constant.
Yes.
So that doesn't actually tell you.
But the codimension increases.
Right.
Because the number of variables increase, so the codimension is constantly increasing. The codimension is n minus dimension.
But you better have depth that's not growing because your curl dimension is fixed.
Let me check something.
I mean, what you're saying is right, but your curl dimension is constant. So
yeah,
as you vary n. So.
Oh right. Oh, you mean the gap can't be anything?
Yeah, it can't be.
Yeah, that's a good point. I wasn't thinking about that. The proof doesn't think about it that way. So yeah, that's right. Sorry, the proof of the ratio does just use that fact essentially, but the proof of non-Cohen-Macaulayness. Now I remember the proof of non-Cohen-Macaulayness is via Reisner's criteria, right? That's right. So you can prove via Reisner's criteria that this is not Cohen-Macaulay, because you can the link of a vertex in a random graph is itself a random graph, and you can show that that random graph has homology with probability 1 in sufficiently reasonable regimes. That's right. That's the proof.
Thanks.
Yeah. Can I ask a related question? Have you thought about other extremal Betti numbers? These.
So sorry, ask the question again.
Like these extremal Betti numbers where you're like non-zero, but if you look to the right and down, I guess you're.
Oh yeah. So I haven't. You can definitely figure out where this ending point is, if that's the question. I don't know if the question is the value or where it ends. I think where it ends is actually pretty straightforward, asymptotically. What we do know from the original results is actually this whole first row, which is allowed to be non-zero. So this first entry, which is allowed to be non-zero, is non-zero. So it's causal, so it can't have non-zero things below that, but these are all non-zero. I don't know exactly where this ends because we didn't study it, but you should be able to nail down where each row ends with some accuracy. The question, there's a little bit of a finicky thing here, which is again, oh sorry, I should really say these things up here are non-zero, down here it's not, down here it's 0. I don't know what to think about this fact yet. So I would say to most people that I think the regularity should be R in this case. In that I think it actually honestly, the entries below here are 0. But I can't rule out that sort of the sporadic entries down here that just continue moving off to the right. We couldn't figure out any way to rule that out. And so it'd be really cool if someone could prove for sure that there are no entries here. So it's worth noting, let me go back to a very early slide. It's worth noting that this result is very close to that, but as far as I can tell, it's in a different regime for P. So they're in the edge ideal case, and so they care about when P is small for an edge ideal. So that's when, for us, when P is almost 1, and that's a regime we didn't study. So they prove a regularity result in that case, but we don't have a regularity result in our case. But otherwise, I think the extremal entries are, the extremal entries over here are very well controlled by this result, the details of this result. The extremal entries on the right, I don't know, but they should be controllable.
Okay, thanks.
Sorry.
All right, let's thank Jay again. Very nice, Jay. Thank you so
Thank you.
much.
Let me stop sharing now.